So now that you know how the attention model works for text, and last time we used the word Leica and did self-attention on it and encoded it, we can do the same for vision. And the key paper here is an image is worth 16 by 16 words, transformers for image recognition at scale. This is a big paper from Google Research and Google Brain. It covers a lot of ground using their hardware and their data, picking up on ideas that have been around in the community. And doing the encoding is actually quite straightforward. There's a picture here that summarizes the approach. The idea is to take an image and break it into patches. So in this case, we have 9 patches. And then run those patches through a linear projection, add some positional encoding, and then run it through a transformer encoder. And finally, you can look at the class token, which is just an empty, noisy image, if you want, or an image patch that you can use to classify things into, in this case, bird, ball, and car. And here, this would be probably a building or something like this. So the transformer encoder is very similar to what we've seen in the Attention is All You Need paper. It's a multi-head attention that is followed by an MLP layer, and this is done multiple times. So to do this, we will first look at how to encode an image and turn it from 2D image into patches, then run it through the linear projection. And at that point, it is very much the same as the characters were. So when we had the word Leica, we had 5 characters. So this would be the L, the A, the I, the K, and the A. They get encoded. We used a 28-dimensional one-hot encoding scheme. In this case, the images are a little larger. There are 16 by 16, so 256 pixels. So you have a 256-dimensional encoding. If you would consider black and white images, here they use red, green, and blue. So you have 3 times 256 is 768. So you see the data is a little more. Obviously, this is more information. But other than that, the transformer encoder doesn't really care about the dimension, as we have seen. So before we move on, have a quick look at the equations here. What it does, it brings the image into these patches. In that case, we had 9 patches, so n would be 9. Each of these patches are run through a same big matrix, and there is a final class encoding, or a single patch that will serve as what has been the space or the point in our previous exercises. Then the whole thing is run through a multi-head self-attention. They use the acronym MSA here. This is the layer norm, and then runs through a multi-layer perceptron. Now, the encoding, or the patch encoding, as we said, is 768 dimensionality if you assume 16 by 16 patches. And so in this case, you would have 9 times the dimensionality, or the number of classes, which are the colors, times the embedding dimension. And so the E matrix is just a very big matrix. All right, so to start, we will do the following. We will create a new notebook, and we will go and take the MNIST dataset, which is a very famous dataset from that is available inside Torch Vision, and it is just showing hand-coded numbers. So we can, I just copied and pasted some boilerplate code to import it from Torch Vision. Then we can do our manual seed as always, set at 42. We can define the image size that we want. And you will see later this is necessary because we can reshape our images in any shape we want and upscale them using the Torch library. We want to use a batch size of 4 just for now. And now we can define a transform that will transform all of our images as we load them. So this is a Torch Vision library, and we imported this here, Torch Vision transforms as T. So I can compose this, and you have to provide a list of things you want to do. The first thing is we want to turn it into a tensor, so it's going to be consumed by PyTorch, and then we want to do the resize, and then we provide image size here. Alright, so let's see if we have everything we need. So we need another parenthesis here, and we can close this, and let's see if this works. Yes. And now we can load the training set, and we use the MNIST library from Torch Vision, and we have to just provide the root, and this has downloaded into one directory above into the datasets folder. So now we have to provide some additional parameters, so we download it and we provide the transform that I just implemented. Let's see what this does. It will download the MNIST data. Now we can define a train loader, and this is a data loader that uses the train set. We want to shuffle it, and we want to use the batch size that we defined above. So with this, we can grab our next or first MNIST example. We have to put an iterator around the train loader, and we could try to run this to see what we get. And you see we have a 32 by 32 image, and we have batch size of 4. Now here we will have the labels, and in this case let's print the content of this. We will have 4 images, and they will have the numbers 6, 4, 7, and 6 on them. So we can now show them with matplotlib, and I will copy and paste this because this is something that you can very easily do here with Gemini. And what it does is it gets the images out of the first part of the batch and the labels out of the other, and then creates subplots, here 4 of them, and essentially just displays the images. So we see we will get 6, 4, 7, and 6, and here we are. So this is the data we want to start with, and now think about how to break this into image patches. Okay, so for doing this we need a couple more tools, and I always put everything into the cell so that you can run things without running everything above. So we want to have the neural network library, we want to have matplotlib, pyplot, and we want to have numpy. So I'm also making sure I define everything that I will need further down. And so in this case, we want to break this image down into 4 patches of size 8 by 8. And we have 1 channel in this case. So other images might have 4 channels. And so here this should be an equal sign. So what we now can do is we can use Torch framework to create a patch class, which will take in the image and return the different patches. And for this we want to pass on all the information about the image and the number of channels that we just defined. We need to call the init function of the superclass and copy some of the information over. So it got that, that's great. And now comes the forward function, where we want to actually breaking our images apart. And so in this case, we expect an image to come in a 4-dimensional tensor, which was the batch size, the number of classes, so this was 1 in our case, and then the height and the width, which was 32 by 32. Now what we can do is we can use the unfold operator that comes with Torch, And in this case, we want to unfold this in 2 and break it into 8 by 8. So in this case, I could say 1 here, but the patches have to be quadratic, so I actually enforce this here. And then we can unfold it again. And it already suggests this here. So this is along the second dimension, and this is along the third dimension. So 0, 1, second dimension, and then we want to unfold along the third dimension. So we can now flatten this, and then we will need to transpose it. But before we do this, let's just write down what we think the dimensionality is. So in this case, we still have the same amount of batches, we have the same amount of classes, but now we have not 2 dimensions for width and height, but we have the patch dimension, which is in this case 8 by 8, and then 8 by 8 again at the end. And so when we flatten this, we do this at the second dimension, 0, 1, 2, and we can then, what we get is, we get B, C, and now we get P row times P col times P height times P width. So what happened here is we took the last 4 dimensions here, so everything after the second one is being wrapped into a single dimension and essentially stacked up. So now we want to do one last step and transpose it. That is, we swap the last 2 rows and we basically put the class at the last dimension. So it will look like this. Now we can see how this would look like if we run it. And for this, we instantiate a patch using our image size and our patch size that we defined above, and the number of channels. Then we can extract the patches, and this is something we want to do without gradients. And in this case, we essentially just run our images through this. Now, what are the images? So far we have images, so we need to turn this into the right data type, and in this case we grab the images, we grab the first image and then we unsqueeze this, so we have the batch dimension again. Alright, so we run this through so we take a single image, run it through our patches, and now we should visualize it, and for that we have to remove the batch dimension. So we do this by squeezing it at the beginning. So now we have a reduced dimension that we can draw. And now we have to also turn it back into something that has patch size 0 and patch size 1. So in this case, it's an 8 by 8 image, and everything else is gonna be put here into the first dimension where the -1 is. And so in this case, we have only one class, so this will be empty. All right, so now I can copy and paste some code to plot this, and let me just do this right now. So what we do is we compute the number of patches, then we create the appropriate number of axes. We then go through 2 for loops and basically show all the individual images. And so here we go. We have a 4x4 grid, and in this case we have 16 patches in total. Now let's try this with some other values. For example, we can also bring it down into a 4x4. This will get us 8x8 and 64 total patches. So you see, this is what we get, 8x8. Or we can also use bigger patches, 16x16, and we get 16 patches. So what we have now done is something that we can use in a PyTorch framework and essentially do what has been done in the Vision Transformer paper, which we have seen here, and basically break down our images into patches. So the next step is to actually multiply an embedding onto all of these individual patches, which we can do here, or which we see here. And we can implement this by creating a new class, which we will call patch embedding. And we can actually copy and paste a lot of this here to save some work. And all right, so what do we want to change? So first we want to call this patch embedding. And now we want to add another variable, which is the dimensionality, which we want to do that. And so in the init routine, we also want to copy this over into our class. So what we now need is a linear projection, which is this E matrix in the paper. And we can just use the neural network toolbox linear module and basically use the dimensionality of our patches. So this is the patch size 0 times the patch size 1 times the number of channels, and the output is the dimension of our model. And we also want to add the fact that the bias is false, because otherwise we would have a full neural network that has a bias term as well. Now in the forward method, we do the same thing. We first do our unfolding. We also keep our flatten and our transpose, but we do one more thing here. Before we do this, we actually apply our linear embedding. And in order to do this best, we grab the actual size of our data. So it already suggests to do this here. We are basically getting all of the information out that I just showed you here. And now we reshape it one more time and use these new information. But this time we actually want to store the patches in a vector. So instead of having a 4x4 or an 8x8, we want to have 64 elements in one dimension. And we do the same here for the height. So here we have the rows and the columns, and here we have the patch height and the patch width to reshape this data. So what did it recommend here? Not sure this is true. Let's leave this out. And now we can add our linear projection like so and run it through this linear projection. Now the same thing happens. We just flatten it and transpose it. And the final thing before we return it though is we want to make sure it is in the right dimension. So we have the batch dimension, this dimension we don't know, and we use the dimensionality of our model. So we can test this now by defining a dimension like 64, and we have to just add this here, the model, and of course this is called patch embedding. So let's see what happens when we run this. This works, and now we should be able to run this through our embedding function, through our visualization. So to visualize this, this doesn't work directly when we run this through here. There's a mismatch with the dimensions, and to better understand this, we can look at what actually comes out of our new patch embedding. So let me just uncomment this here, and now we can see that the shape is having 64 at the end. So we have 4 images which each have dimensionality d model. So in order to turn this into something that we can display, we want to squeeze away the first dimension here. So this batch dimension goes away, but then we want to resize this into, or in this case using the view operator, into an 8x8. In this case, the dimensionality of the patch size was 16x16. So in order to really use the d model parameter, we would need to use the square root, and so we can say d model square root, so power 1/2, and the result of this is 8. So this should work, and when we now look at the shape, we will get 4 images that are of size 8x8, and these we can now run through our model. So in this case, you see this is completely random because we have been using a linear projection with random weights, but now we do have something that is trainable and that we can use as has been defined here. So we basically multiply each of these patches with the same matrix, and in this case we are not doing the position encoding just yet. Before we do this though, I want to show you one different way of doing the patching embeddings using a 2D convolution. You can get the same result with a convolution operator, which is much more efficiently implemented on the GPU, and so doing it this way is really a little bit silly because it does a lot of not very efficient things. So what we want to do is we want to do a convolution which has a stride length that is the same as the patch. So in this case it's an 8x8 pattern and an 8x8 stride length, so the convolution operator would jump, and we have to take our E matrix, here the linear embedding, and turn it into convolution kernels that do the exact same thing. So in order to do this, we create a new class, patch embedding, and we can copy and paste everything from above. So in this case, we have something like this. This is the exact same thing that we've done before, but this time we define a convolution operator, and we use the same variable here, but this time we use the conv2d operator from Torch. And so here we have the in channels is the number of channels, the out channels is the dimensionality of the model, so we will get 64 out channels. The kernel size is the size of the patches. Now we tell it to use the stride size to be the patch size, so the kernel will actually jump from patch to patch. And we also want to remove the bias, just as we did before, because we don't need to have a full neural network, but we just want to multiply with the patch embedding. And so this is a little bit tricky because you have 64 channels. You basically take one channel, one image, and you turn that into 64 different images. This is not the same as we've done earlier, but you will see how this comes along once we implement the whole thing. So for the forward function, we just run this linear projection, and maybe it will help to think about real quick what we get. We have the batch dimension. We have now 64 little images, and each of those are the size of the patch size. So we have essentially 64 little images that are 8 by 8 in size. So we can now flatten this as well. In this case, the images are turned into a single column vector by just flattening everything starting from the second dimension. And we finally do a transpose, so we do get the output. And in this case, this is the patch size, and this is the model dimension. So now we get the exact same thing. If you remember, this was 64 here at the end, and this is what we have here as well. So we can directly return this and see what happens. So something is missing here still. Maybe running this will shed light on this. Oh, this is just the indentation. It should be here. All right, so this should work. So we define this, and we can now use the same code as here to test it. In this case, we want 64. And we can visualize it, and we should get something equally random as before. So if you're interested, this is worth digging in a little deeper to understand how the patch embedding function that we implemented here is doing the same thing as Unfold by using the convolution operation. This is just something that you would generally use because you can use the full power of the GPU. All right, so with that, we move forward in our implementation of the vision decoder. If we continue to follow the paper, we now have the patch embedding. We will need positional encoding, and here we can again use the same approach as attention is all you need. And I can already tell you in practice this will be much easier done by using a learnable embedding. It is interesting to do it this way because then you can visualize how the embedding would look like, and then later validate or see for yourself how the learned one will look very similar. So in this case, we want to have we want to provide the dimension of the model, and then we have to provide the maximum sequence length. And in this case, this would be a 3 by 3 or 9 different image patches. Depends on how much you cut your images, of course. So let me just do some of the coding here. And now the first thing we want to do is we want to add the class token, which we haven't defined yet. And in this case, we generate a random patch that has the same dimensionality as the D model. So as you can see here, the class token has the same dimensionality as these guys. So this is the dimensionality of the patches after they've been transformed by the linear embedding. So you see this is exactly the same thing here. We create a a random matrix which is of dimensionality d model. Now we want to add the positional encoding, and in this case we use zeros and we use the maximum sequence length, and so we have let's say 9 different patches, and then we have the model here. So now we want to populate our matrix that contains the positional encoding, and we do this by using a nested for loop. And here, I don't know where that comes from. I want to do it this way. I want to just go over the model. And now if the index is even, then we can assign this to the sine function. And here again, we want to use some kind of large period length and use I divided by d model. This should do the trick. So now I'm essentially adding some form of sine, and then I can do the same thing, but I want to do this with cosine. And also I want to shift this by 1 because these are the odd numbers. Now that I created this, I want to register this as a buffer. So Torch is not actually computing gradients for this, but actually just uses this as data. So with that, we can define our forward function. So we've created one class token here, but this operation or forward function operates on batches. So we actually need to expand our class token to cover all the batches. And in this case, we use the expand function, and then grabbing the first the size of the input, and the first dimension is the number of badges, and then we can distribute this over the rest of the, and so these are the dimensionality of the original class token. So we have the model, and we want to now add this to the beginning of every batch. So we take our tokens for batch, and we concatenate it with the input that we are getting, which should have the same number of batches, and we do this across the second dimension. So not dim equals 0, but dim equals 1. Now that we've done all of this, we can okay, so now the cut operation is correctly written. We can add our our positional encoding. All right, so let's see how this looks like. Now we can do everything as before and define the different aspects of our transformer. So you will see that these are the exact same things that we've done before. We have an attention head. We have linear embeddings for the query, the key, and the value, which we apply here in the forward function. Then the attention is the dot product between query and key. We then divide, normalize by the head size or the square root thereof. We run this through the softmax function, and we multiply with the value. We can also do multi-head attention, and here we use something a little less sophisticated than previously. We simply break the attention head into different heads. So you see here I divide the head size is the model dimension divided by the number of heads, And now I'm using the attention head that I defined here, and I just do it as many as I have heads and concatenate them this way. So in my forward function, I simply have to go through the heads and then concatenate them back to get my original model dimension. And finally, I have a linear model that sits on top of the multi-head attention. So with this, we can go on and define our transformer encoder. And so here again, there's nothing new. We are using the same functions as we have implemented before. So in this case, the transformer encoder has the layer norm, it has the multi-head attention, it has another layer norm, and a final multi-layer perceptron at the end. This has, as before, two linear units with a gated linear unit in front. And so when I do the forward step, all I do is running it through the multi-head attention and then running it through the multi-layer perceptron. We can now go back and compare this with the paper, and you will find that we have the exact same equations here. We have the multi-head attention, self-attention, and then we run it through a final MLP layer, and we each time carry forward these residual connections. So you will see the same thing happening here. I'm adding the residual connections and running it through the layer norm. So with this, we can create the vision transformer class, and this has again a lot of text, but nothing fundamentally new. It's really doing the same thing, except that this time it's running it through that patch embedding. And here we assert that the image size is divisible by the patch size, otherwise this doesn't work. We then use our patch embedding, we use our positional encoding, and then we use the transformer encoder that we have been defining above for the number of layers that we want to use. So you see, this is pretty straightforward. The patch embeddings create a bunch of patches. We add the positional encoding, we run the whole through the transformer encoder. But here, when we use the final MLP layer, which is this multi-layer perceptron, we are actually dropping all but the first patch because this is our patch embedding. And so this is something you can see here. In this case, we are running the MLP head, or we're only using the class patch in our actual classifier. So with this, we should be able to run all of this. And let's define a couple of parameters. So first, we want to use a rather simple model dimension. Let's say we use, because we have only 9 different classes, let's keep it simple here with the model dimension. We have 10 classes, which are starting from 0 to 9. We have the image size 32 by 32, and this is actually a slight upscale from the MNIST, which is 28 by 28, but we want to use something that is actually easier to break into quadratic patches. We can start with patch size 16 by 16. We have 1 channel. We can start with 3 heads and 3 layers. We can use 128 images in 1 batch, and we train for 5 epochs with a learning rate of 0.05. Actually, let's do 0.005, which is even smaller. So let's copy and paste some stuff from above, but now this time I also add a test loader. So here I have my training set from MNIST. I also use this as the test set, and now I shuffle this, and I can use both of these during training. There's one thing we haven't imported, which is the optimizer. So we use Atom and we can now define our device. And so in this case, I will use CUDA if this is otherwise the CPU. And it actually knows already what I wanted to do. I want to use my new vision transformer. I want to use dmodel, n classes, and then I want to use the image size and the patch size and the number of channels, number of heads, the number of layers, and I want to send all of this to our device, whether this is CUDA or, and maybe now it's a good time to switch our done. Is this? Let's use the T4 GPU. And for this, I probably will need to run a lot of these things here again. And now I can instantiate my model. Of course, I need to run all of these guys. So we started with the patch embedding. So maybe we should just copy these here. See, this is why I always want to do this. And we don't need any of this. So this works. The positional encoding is back. The attention head is back. The multi-head attention, which is using the attention head module, the transformer encoder, which puts all of this together, and finally the vision transformer. And we should be able to continue with our training. So the model is loaded. We can define the optimizer. We use Atom. We use the parameters and the learning rate. And so in this case, I want to call this transformer here as well. I want to use cross entropy loss. And now train my model for the number of epochs. And now let's keep track of our training loss. Initialize this as 0 and go over the train loader. And we can grab our inputs and our labels from the data. So you remember, these are the images, these are the labels, and we have to transport all of these to the device. Optimizer 0 grad is also a good thing to do. And now we can use our transformer and basically transform all of our images. Now the loss is the criterion we defined, and we use the outputs and the labels. So this is the cross entropy loss. We propagate this back. We run a step for the optimizer, and we store the loss from the last iteration as training loss. So now we can print all of this at the end. And let's say we want to output our epoch. Say how many are still remaining, and loss, which is the training loss, divided by the length of the train loader. Here we want to add some precision, not to get too much data. So we can start running this, and this should run on the GPU. Of course, it doesn't work. Let's try to catch this with Gemini. Well, this makes a lot of sense. I actually want to add the PE and not the parameters. This is typical problem from autocomplete. Let's accept this. Now we have to, of course, rerun all of this stuff in order to build the model. And now this should work. All right, so this is training. While this is training, we can start writing the test function. And let's just make a little counter that counts how many of these guys we are classifying correctly. We do no-grad for data in test loader. That's right. We do get the images and the labels. We bring them to the CUDA device if necessary. And so in this case, we do that also for the labels. Now we can simply run our images through the transformer. We get the output. We now want to see our predictions. And in this case, we actually look at the data itself of the output, which are these numbers. And we take the maximum number here. Well, this is surprising to me that it really wants to do exactly this. And in this case, we use the correct ones, which are those which have the exact same name labels as we predicted. We sum this up and we get the final number. And so all that is missing is now to print out the model accuracy. And so we say 100 times the correct numbers, and then we use an integer division by the total. And this should work. And so we do get 92% accuracy on our VIT encoder. Now, is this a good number? We should get 99.99% using very simple neural networks. When you go back to the paper and look through this, you will see that the image decoder or the vision transformer actually doesn't work as well as a neural network when the model size is small. So what they do here in this paper, they have a lot of different VIT base, which has 12 layers, and then VIT huge, which is 32 layers. It's 632 million parameters. And it turns out that when you look at the results, and let me see if I can find this here, they do beat the standard, ResNet-like classification neural networks by a very small percentage. You see here we get with VIT huge, you do get 88.55, whereas ResNet only gets 87% accuracy. But this all is done at much faster training. So here they use 2,500 days of TPU training versus 9,900, so almost 4 times as much when training the ResNet. So you see, even though the performance is just a tiny bit better, it trains 4 times as fast. But what I'm actually after is when you look at the training size, you will see that the transformer VIT are these round guys here. So VIT large is here. But this is actually not as good as the ResNet implementation until you use a very big pre-training set. So as the pre-training data set gets bigger, you see that the vision transformer really plays out its full potential, and it actually beats the ResNet-like implementation by quite a lot once you are really using 300 million images for pre-training. If you don't have that, but just 1 million images, then the neural network is actually much better than the transformer. Now, we are using only a few thousand images here with MNIST, and so we have no chance to get the transformer to actually do this from scratch in a way we want. So I think you will see these kind of results throughout this paper here. When you look at these results, you really need a big number of data points in order to train the vision transformers. Here is an interesting picture as well of the position embedding that got trained. So you see that even if you don't use sine and cosine, the learned position embedding actually shows some interesting patterns that correspond to the position. And there's much more other interesting information here in this paper, so it's worth a read, especially in the appendix that follows here after the end, where you see not just more details on the equation, but a lot of ablations on different data sets, and also how the vision transformer is different than the state of the art at the time.